Check it out.
Not on YouTube. Still gonna be another minute.
Well, the
Actually, yeah. Try joining the Hangout and see if.
this is live,
Let's put that on.
starting soon.
But what about the actual Hangout, not on YouTube?
Yeah, that's what I'm looking at. Says it doesn't like my browser. Okay, I bet you it's working. Just my browser is this big.
Okay, I'm holding you to it. I'm gonna hold you to it because we're gonna start. If you think it's working.
Maybe someone else check this.
No, that's fine. We'll give it like one more minute just to give people a chance to sign on. And get started.
We did have a thumbnail that was your screen.
Ooh, that's promising.
So
All right, let's get started. We're a couple minutes after, so let's begin. Welcome to Study Group, everyone. Today we're going to talk about reproducible research in Docker. So, show of hands, who has been to dependency hell lately? Anybody? Anybody? Jeff has. Anyone else? So for people unfamiliar with the term, dependency hell is when you want to use some piece of software, and it's got a bunch of dependencies. So you go and you try to install them all, but one of them doesn't work. One of them, you got to update, I don't know, Xtools. Or you get a new C compiler, or I don't know what. The dependency has another dependency. So say, okay, no problem. I can follow this rabbit hole. I'm gonna go install that other dependency. And it works, but it breaks something else. Now some other dependency doesn't work. And to get both of them to work at the same time, you need some special operating system configuration, and you gotta fiddle around with things. And all of a sudden, 3 days have gone by. You have not run the software you wanted to run. You have not got any real work done. You have just fiddled around trying to get things installed. You're successful. Hello, Amy. You finally get things installed and working, and the results of the software you wanted to run are so successful that 7 of your colleagues want you to help them install the same stuff on their computer, and they all have different operating systems than you. Welcome to dependency hell. This is something that eats up tons of time when we try to use software that we share amongst ourselves. Something that I have said and that lots of people in the open science movement have been advocating lately is the huge importance of sharing our code and our analyses open source so that we have a record that lets us reproduce these analyses in the future, and so that as a collective discipline, we can start building up this toolbox of tools to use so we don't have to start from zero on all of our analyses every single time. Anybody that knows me is absolutely sick and tired of hearing this speech. They've heard it a million times. But there's just one fly in the ointment with that open source argument, and that's that code does not run in a vacuum. If I write some code, it will not necessarily work the same on your Linux machine or your Windows machine as it does on my Mac. Things will depend really strongly on their context. Fighting with that context, trying to get things installed so things work consistently across machines and across collaborators is a giant waste of time. It's frustrating, it's tedious, nobody likes it, it's not easy for anybody. And as I am very fond of saying, your time is worth more than fighting with dependencies. So we mustn't do that. We must find a way to avoid that trouble. So it'd be really cool if we had some tool that would encapsulate our operating system that we're running things on and all the dependencies that we're using to contextualize that code that we're running, and let us share that encapsulated context of our code with our collaborators. Our most important collaborator, of course, being ourselves years later. when we want to rerun analyses we've done in the past. Turns out other people have had the exact same thought, and that's exactly what Docker is. Docker is to dependencies and operating systems what Git is to code. It lets us wrap this stuff up, archive it for later, share it with our colleagues in a way that's completely consistent every time. So how does Docker actually pull something like that off? Well, what it's doing is it's running a thing called a Linux container in the background, which you can think of as this like little bubble universe which has its own operating system and its own stack of dependencies installed on it, so that no matter who runs this Docker image, whether it's on a Mac or a Linux machine or Windows machine or whatever, it's actually running the same little encapsulated operating system and set of dependencies every time. So we can be sure that everything's going to work the exact same way every time we set it up, no matter who sets it up, no matter what computer we set it up on. Super convenient, super reliable, helps with reproducibility in our research. So, I mean, that's the sales pitch. That's like what Docker is all about. Let's start pressing some buttons. So I asked you all to download Docker and get that installed as a prerequisite for this lesson. My friends on Windows and Mac would have also got something called the Docker Quick Start Terminal installed along with that. So fire that up to begin with, and it will open something that looks a heck of a lot like a normal terminal window with this adorable little ASCII whale to tell you that it has launched Docker. If you're on a Linux machine, I think you can just do this straight from the command line. So there's no special shell you need to open at all.
Sudo,
you have to sudo? Okay, there you go. Sudo into that, and you're good to go. So everyone fire that up. Make sure you've got a Docker appropriate shell set up there. And you can tell if it's worked correctly by checking the other dependency that I asked you to install as the second and last dependency of this lesson. And that is to go Docker images, which should list all the images that you have on your machine. Now I've got a bunch here. The only one we actually care about today is this rocker/OpenSci thing. So I'm gonna chill out for a second, let you all catch up with that. Does everyone have that? Anyone not have that? Okay, cool. Going once, going twice. Okay, so we all have that. So what these Docker images are is like the basis that you're gonna build your dependency stack on. So like I said, Docker encapsulates your operating system that you're gonna run your code on and all its dependencies in this little bubble universe. And the easiest way to think about this as we build these dependency stacks up, I like to think of Docker like baking a pie, actually. And it's made in, like any good pie, it's made in layers. What's the first layer of our pie we gotta have? A crust, yeah, exactly. You gotta have a crust for your pie. You gotta have the basis that you're gonna build everything else on. This Rocker R OpenSci thing is the basis that we're gonna build this operating context on. The formal jargon term for this is a Docker image or base image. And base images contain typically a couple different things. First thing they contain is an operating system that you're gonna run this stuff using. Second thing they typically contain is a set of common dependencies that you're gonna wanna distribute with this. How you should think of this base image is like this little virtualized computer that runs just like a normal computer, but you can copy it because it's just software off to your collaborators, off to yourself in the future. Question? This is subtly different from a virtual machine. So actually on a Mac, like you and I have, you are actually running a Linux virtual machine. And in that virtual machine, you are running a Linux container. And what is the difference between a Linux container and a virtual machine? Not much, except a Linux container is very, very lightweight. So rather than being a big resource hog like a lot of virtual machines are, Linux containers are very, very light. They're also very, very well encapsulated. So that's why I keep calling it a bubble universe. Anything that happens inside that Linux container is a priori isolated from your actual physical machine. Comment.
I was just going to ask, what's special about this Rocker or OpenSci? What kind of stuff does it contain?
I'm getting there. That's exactly what's special about it, and that's what your crust is made of. Is it a graham cracker crust? Is it a phyllo pastry crust? So in the delicious graham cracker crust of Rocker R OpenSci, you get the following things. The operating system is Linux Debian, so a very lightweight Linux build. On top of that, you have the entire Hadleyverse all pre-installed on that. So of course you also have base R with that. You also have every single R OpenSci package that's on CRAN is pre-installed on this image. And you also have RStudio on this image. So all that stuff comes pre-packaged for you in this base image.
Does it come with like DevTools and stuff like that?
So no, probably not.
It is Hadley packaged. I'm just sort of curious because that one's usually a bit more.
If it's the docs say it has the entire Hadley verse.
Okay,
So
okay.
you interpret that as you will. You know more about R than I do. So take it away. That's what it has. If it doesn't have what you want, later in this lesson, we're going to learn how to fix that. I'm going to add the things that you do want.
The versions frozen or like?
So actually, another thing we'll see later in this lesson is that Docker automatically versions your pies as you bake them. They automatically version these images as you build them up. So another thing we're going to see is that in order to share these images, there's a service much like GitHub called, you guessed it, Docker Hub, that lets you share these images amongst people. And that, again, has versions of these images that you can sort of rewind through history through. Anyway, okay. So that's what this is. That's what this Rocker R OpenSci thing I asked you to download is. It's Debian plus a bunch of R packages. Let's fire it up. So to actually run a Docker image, we do the following. Let's see if I can find this here. Oh, actually, yeah, let's start with that. So we do Docker run -dp. My giant font is going to make this run off the end of the line. Sorry about that. A7, colon, A7, A7. And then the name of the image, rocker/R OpenSci. That should work. You get a big, long, ugly hash, and that means it's done things correctly. So what this image does, in addition to, so when you did that step, what you did was effectively like turning on your computer, turning on your virtual computer. So it started Debian, and the other thing that this image does is it starts broadcasting RStudio at a particular IP address. So now what we got to do, if we want to actually interact with RStudio, is find out what that IP address is. So we can go look at it in our browser. So for my Mac and Windows friends, if you do docker-machine and then ls, you will get a list of all the virtual machines that is running these Linux containers in them. And the IP address you want is under the URL column here. So mine is 192.168.99.100. Notice we do not want the port. We just want the IP address. For my Linux friends, to find the IP address that you want, there's a very long command, which rather than typing it out for you, if you look in the Blackboard behind you, there is a link to all the notes for this tutorial. So if you head on in there and look in section, drumroll please, section 2, there will be a line you can cut and paste to get the correct IP address on your Linux machine. I'm just going to share that URL with our internet friends right now so they know what I'm talking about. Grab this, go over here. I'm going to put that, internet friends, I'm going to put that in the chat right here. So that's the link to the notes I'm talking about. It's pretty gross, I know. Right. I do not. So once you grab that URL, or not URL, sorry, IP address, head on over to your favorite browser, fire that on in, well, not that one, fire in the IP address that you just copied. Copy it again. And then go colon 8787, and you should see, an RStudio sign-in page. Excellent. I'll pause for a second while everyone catches up with that. For those that just wandered in a few minutes late, hi Andrew.
Sorry.
If you look behind you, there is a URL that leads to the notes to this lesson. So we have gone through the getting set up stage and have just launched our first container. So
That's cool. So that's running your local machine.
Yep. How's everyone doing? Does everyone have our studio sign-in page? Going once, going twice? Yeah?
Not
Okay,
quite
cool.
yet.
Oh, no. Okay, a couple more seconds.
You just paste in the IP address.
Yep, and then colon 8787.
Okay. There we go.
Yes, excellent. I was like 90% sure that Linux command would work. So I'm really glad that it actually did.
Around both of the Docker things.
Okay, you got to send me a pull request to my notes later so the Linux people can get it. Cool. Okay, so now that we've got our RStudio sign-in page, our username is RStudio. Your password is RStudio. Super secure. Get on in there, chug, 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 and you've got RStudio. Awesome. Not only do you have RStudio running in your browser, as promised, you've got the entire Hadleyverse all set up and installed there. So if I do something like library, what have you guys taught me about? dplyr. I do library dplyr like that. Boom, there's dplyr loaded. I did not have to install dplyr explicitly. I did not have to chase down any of its dependencies. I did not have to do that for any of the Hadleyverse or our OpenSci packages that are all pre-installed in my little Linux container here. The other thing that the other point that I really want to drive home here is that this is RStudio that you know and love, but it absolutely is not the RStudio that you probably had pre-installed on your machine before we ever did this lesson. This is a fresh, brand, shiny new install of RStudio with all those dependencies pre-installed with it that you spooled up solely by starting this Docker image and everything all set up for you and ready to go. So that's cool. We've got the Hadleyverse. What else do I want? Let's do, you guys can't see the bottom of my screen. Hey, let me move that up a bit so y'all can see. So what else, what other packages do we like? I like, we're at UBC here, so we're all fans of Jenny Bryan. So let's load Gapminder. Fire up Gapminder. Oh, error. Oh no, there's no package called Gapminder. Damn it. We don't have Gapminder installed in our stack of dependencies that we installed beforehand. Once we start with our graham cracker crust, of course, that's a pretty terrible pie, right? Pies need more layers than just the crust. So the next step that we're going to go through in just a minute is how to add more custom dependencies to our Docker image. That's how these Docker images are built up in layers like that. So we got our base layer. We're going to add custom layers on top of that in just a minute. Before we do that, though, we need to learn a little bit more about how to manage these Linux containers that are running on our machines now. So we all started this Linux container that's running like all our OpenSci packages and RStudio and all this good stuff. If we want to see the packages that, not packages, but the containers, excuse me, that we have running on our machine, we can do docker ps-a, and we get a list of everything that's running on our machine. Mine is super hard to read because my font is so big, but you should see that on one line where maybe I'll just make it a little bit smaller just for now. Try that again. Nope, still too big. Okay, well, you can see it on your machine, where you get a bunch of stats about the containers that are running right now. So these you should imagine as like computers that you've spooled up and are running as little virtual computers on your machine. In order to kill one and turn that computer off, we can do docker kill, and then this thing under container ID in that thing you just listed. So if we do that, that's like turning off the computer that you started. And if we do docker ps-a again, we see that where previously it was up, the status said up for however long, now our status is exited because we killed it and turned it off. If we want, oh, the other thing though, is that even after you turn those instances off, they will hang out in that list forever, which is not a big deal when you have 3 or 4. But when you have 3,000 or 4,000, it gets really kind of exhausting to look at. So to remove old junk, old containers from that list, you can do docker remove, and then that same container ID again. Removes it, and then if I do docker ps-a again to list, there's nothing left. They're all gone.
We remove like all of them.
You will learn that command before the hour is done. Because yes, when you have a whole bunch, you do not want to have to go through that 3-step process to kill and remove them all. But I promise I will teach you better before we're done here today. So that's how you list your running machines. That's how you kill them, and that's how you delete old ones. Pause for a second. Questions, comments?
So why does Docker have so many different instances? Shouldn't I be running just one instance with one machine?
Well, you can run just one if you want, or you can run many. So it's not really Docker doing it. It's kind of up to you, however many you start.
Okay, so in this case, why do you have so many?
You have 4. I'm shocked. I don't know why. I have 1.
Are they like if you ran it before or something, just like a test? Because I have a whole bunch. 'Cause I was
Yeah.
testing things out.
Exactly. So if you were fiddling around with things as part of the install and setup steps, you might have a bunch left over. When you run that command that we did to launch stuff, wherever it was, that launches 1, exactly 1. So we probably did a bunch of that during setup if you've got multiple ones. Like Jeff was asking about, we're going to learn how to kill them all and delete them all in one line very soon, shortly. Okay, so now that we've launched our first container and run it, there's a few really cool things that happen there that might be a little bit subtle. Notice that we all installed the same Rocker R OpenSci image, and it worked the same way for everyone. It worked on my Mac, it worked on your Linux machine, it worked on your Windows machine, it worked the same everywhere. Everyone did the exact same thing, downloaded the exact same image, and it all worked. That's amazing. Anyone that's taught software carpentry before knows that in a room of 40 people, there will always be 1 or 2 people that cannot install their dependencies. It's not their fault. They didn't do anything wrong. It is really hard to write code that runs on every single operating system under the sun. It's basically impossible. So we've had experiences with that. So what Docker is providing for us, as I advertised at the beginning, was that even though we all have these different operating systems and different versions of whatever, we're all actually running Debian Linux. We're all actually running the exact same version of Debian Linux. So that no matter what this physical real-world hardware is, kind of doesn't matter. We're abstracting that away and running things in the same way for everyone. The other really neat thing that happened is that, remember how to list what images you have? Who knows? Remembers? Docker images, right? Images, like that. So I only asked you to install Rocker R OpenSci for this lesson. That's all we need today. But there's nothing stopping you from having a whole ton of different images. So think about what that means, right? If you need different dependency stacks for different analyses, you can have a different Docker image for each one. You can do your analysis in one, shut that image down, spool up a different image with a different set of things installed on it, totally different operating system if you want, and run some other analysis there. So rather than worrying about, oh, this package I need to downgrade this dependency to this other thing and like fooling around with stuff like that, you can just quickly switch back and forth between Docker images, no matter what stack you need to run your application. The other sort of corollary of that is you're working on your latest paper right now in 2015. You've got a Docker image that runs the analysis for that, and then 15 years go by. It's now 2030. For some reason, you want to rerun that analysis that you did. Now, the computer you originally ran it on is a melted pile of slag in a trash heap somewhere, and you've got a fancy new future computer, but your fancy new future computer doesn't know how to run this archaic stuff that you were doing in 2015. You are in trouble in most cases if you want to rerun stuff, but Docker to the rescue. Of course, you kept all these old images that you made for running your analyses. So you fire up your 2015 image, and it's like a time warp. It's like a portal back to 2015, and you can rerun everything exactly as you did back then with one command, just spooling up a Docker image. That's the power of Docker that we've got just a little hint of here so far in what we've done. Okay, cool. So as advertised, what we've done so far is just the graham cracker crust of our pie. We want to start adding custom dependencies to our pie, to our Docker image. So if we want to do that, we want to bake a pie. What do we need? What do you need to bake a pie? Anybody?
Strawberry rhubarb filling.
Strawberry rhubarb filling. I absolutely agree. That's Gapminder. What else do you need to bake a pie?
Stove.
A stove. That's your machine right in front of you. Another crucial element, of course, is a recipe. If you want to make this pie, you better know how to make it. You have to teach Docker how to put these layers of operating system and dependencies and custom dependencies together. How we do that is via something called a Docker file. So everybody in your favorite text editor, open up a new file called, you guessed it, Docker file. is going to be our recipe for composing our custom image. So the first thing we put in any Docker file is the first thing we put in our pie, which is that delicious crust. We start by saying all caps from the base image that we want to start building off of. So rocker/r open sci, like so. And then colon latest, let's use the latest tag for this. From command is always, 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 always the first command in your Docker file. This is telling Docker what the base operating system is you want to run off of. So in this case, we want to run off of Debian Linux with all that R stuff installed on top of it. Comment.
What's the comment character for this?
Hash mark. Shall we put a comment in?
Yeah, why not?
Jeff wants comments. So hash mark comment our base image from always comes first. Caveat comments, of course. Everyone's got that? Okay. So if that was all that was in our recipe, then we would just still have the base image. We just still have our graham cracker crust. We need our rhubarb, strawberry, banana, fudge, whatever it was, filling that Jeff wants. So banana strudel. Yeah, okay, there you go. So to add that, we use the following couple of commands in our Docker file. All caps run. And what we're going to do here is the most vanilla possible way to install an R dependency. We're going to wget it. So copy this exactly. Run wget https:// CRAN. We're going to grab the source code of Gapminder off of CRAN. So that's like, what's that? rprojects.org/source/contrib /Gapminder _0.1.0 .tar.gz. So that downloads the source of Gapminder, the package we want, off of CRAN. And then we can do, oh, I should have said, actually, these run commands in your Docker file are exactly shell commands. So whatever is after run is a shell command that's going to get executed in the operating system you define in your from command. So it's going to happen inside your little Debian Linux bubble universe there. Then, so we've downloaded the dependency, now we got to install it. So how do you install an R package from the command line? You guys know better than me. It's cmd install, and then the tarball. So Gapminder 0.1.0 .tar.gz, and just save that. There you go. We have added a custom dependency to our recipe. That's going to be our delicious lemon filling to our pie. I'm going to pause for a second there because I hear a lot of chatting. So is there questions, problems? I'll slow down for a second to let people catch up.
Can we say run R as part of the script and tell it to install the thing in there? Let's see from there.
Like with a packages install?
Yeah.
Maybe. My bud Carl Boediger mentioned when I was writing this lesson that he's got something, a script called Littler, which will actually wrap packages install in something you can do from this command line so that it resolves dependencies in the same way that packages install does, because this does not resolve dependencies. You have to do it by hand. So we're doing something. Well, I mean, there's pluses and minuses, right? Now, it's true it doesn't resolve dependencies by hand, but that gives you ultimate controls over what's happening, right? That's kind of the point of Docker. You want a really rock solid stack of dependencies that is consistent all the time and does not change from install to install. That's the philosophy. Of course, sometimes you don't really care. You really just want it to be convenient, and that's what Carl's littler will help you with.
Okay.
To wrap packages install so you can do it from a Docker file. How's everyone doing? Questions? No? Okay, let's move on. So we've got our recipe, we've got our base layer in the from line, we've got our custom dependencies in the run line. Save that. And then back at our Docker prompt, we can build this with the following command. Docker. So once you have put all the ingredients together for your pie, what do you got to do? Yeah, bake the pie, right? So let's bake the pie. Bake the pie with the following command. Docker build -t, and I call this lemon pie. There you go. One weird rule for these, no capitals in the names of these things. I don't know, you just can't. And then end it with a dot that's super hard to see where you're sitting from. Fire that off. Chug, 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 lots of writing. And you should see the last line it prints out is successfully built some hash. Not space then dot. There's the command again. Can you see that? Do you want it to be bigger? Oh. Yeah?
So I can get over CMash Studio instead of browser.
Isn't that awesome?
That is
I'm really impressed with the makers of RStudio that made that so slick.
Yes.
Mhm.
That's really cool.
I'm a little bit drunk with power.
It's amazing, right? Because-
Because give you a hangover.
Well, because look at look at how fast you set that up, right?
Right.
Like if you get a new computer, you don't have to be all like, oh, I need R, now I need RStudio, now I need this bajillion different. No. Fire up that image. You're good to go.
Sell Docker.
Yep. And you got everything you ever needed. Think of the power if you get like a new collaborator, a new student in your group. Not only do they not have to fight with figuring out how to set up your stack, it's a one-step process that gives them a stack that will be the exact same as everyone else in the group. So they're guaranteed to hit the ground running with their stack. Super cool. Okay, we just baked our pie with Docker build -t lemon pie. How do we list our images again? Anybody know? No, whoops. Sorry. Docker images. Like that. Oh, there's lemon pie, or whatever you called your image. And so we can fire that up with the same command that we used originally. So we'll just keep mashing up arrow, where to go. Docker run, but now instead of Docker our OpenSci, we give it the name lemon pie. Like that. Fire it off. Big ugly hash. And what do we do? Where's our studio? How do we get at that? Anybody? Andrew just said it.
Oh, sorry. What was that?
Where's our studio? Now that we started our
Awful IP
at that terrible IP address you found the first time. So if we go back there and refresh it, I'll make my window a little bigger. Got to sign in again. What's your password? What's your name and password?
Double RStudio.
RStudio, super secure. Here we go.
Did you change that? Where would you
Probably.
change that?
Sign in again. Here's our studio. Now, if we do library gapminder, doesn't complain at us, good start. And if I type, well, no, spell it right. Oh my God, it's auto-completing for me. Gapminder. Aha, there we go. There's all the Gapminder data pre-baked in to this image that we just wrote a recipe for in our Docker file.
So did you run the command Docker build?
Yes, so I'll go back to the,
I'm running it and it's taking several views now.
really?
Yeah, it's sending new context to Dr. Demon and now it's also 4 gigs. I don't know what it's doing.
4 gigs?
Whoa, what could you?
I believe you. I believe
I
you.
don't know what it's doing, but it's not sending anything anyway. It's a local demon
Uh-huh.
and it's sending new context. I don't know.
I do not know.
What did you, everything that is saved is like Docker file on the, okay.
And this is all like in the same directory that you spooled up the plain image in? I'm gonna come look at this.
All right, here we go.
So Docker file looks like
That's already amazing. Yeah, what is the -t?
Probably kill it before such a
Because
Because I mean, that miner was like, kill
that's okay.
So it shouldn't be, and the base image is 3 gigabytes. So, that's really surprising. I'm not sure. I don't know.
So I can build everything.
What map
The Hadley
version do you
first is
want?
like 90% of all the.
The latest.
Whatever. it is.
Yeah, whatever. So yeah, I wish I could help you. That's surprising. Work together with a neighbor? I can't tell you.
Is that what you're talking about? Yeah.
Yes.
What does the A787 call an A787?
So keep in mind, we are speaking across 2 worlds here. There's the actual physical world of your computer, and there's this virtualized world of your Linux container. So what your Linux container is doing is it's broadcasting RStudio at a particular port in its universe, but you need to associate that port with a port in this universe, in the physical, like your computer's port. So you need to associate, like I said, a port on one machine with a port on the other machine.
Or just, is that the DP broadcast from 8787
Yeah.
to 8787?
Yeah, exactly. Other people besides you have been frustrated by this. When I was talking to Carl about this lesson, he was talking about trying to find a way to make that a little more transparent and a little less verbose. So that might get simpler in the future. But for now, that's what it's doing. Will. Oh, did you not kill your old one? I bet you didn't. I bet you didn't. Do you remember if you press up arrow, do you still have the kill command? Okay, and if you don't, I'm going to show you how to totally kill everything in just a second.
It says you're not allowed to have more than one at once.
Not on one port.
Okay.
Computers are polite. They do not talk over each other on the same port.
Like, how would you change another port? Like,
Put a different number on.
it can be like any number?
Yeah, sort of. So things get weird with firewall settings, right? Like what ports are available for you to communicate on? I don't know. Is anything else on your machine using one of those ports? I don't know. Yeah. Yeah. So the answer to your question is yes, with a big asterisk beside it. More questions?
How do we access the terminal the Debian instance is running?
So that's one thing that's kind of special about this Rocker RStudio image, is that it instantly spools up a server that sucks up your command line there. So like if you, for example, when you just started the plain image, you saw that it hung with no like return to a terminal prompt, because it's that terminal window is talking to your browser. In a more vanilla Docker image, it would just give you the terminal prompt back when you started, rather than starting broadcasting anything to an IP. That's a little bit fancy, and that's special to these Rocker images. So if you want to see an example of that, I highly recommend the tutorials on Docker's main website that give really simple introductions. They don't really install anything fancy. But I wanted to do something a little fancy because I know this crowd really likes R, so I wanted to do the Rocker R OpenSci stuff, which immediately uses that command prompt to serve from.
Oh, I see. Wait.
I suppose if you wanted the best of both worlds, you can make your own image that starts with the same dependencies, but instead of launching RStudio, you'd launch that as a background process kind of thing. But then you've got to rebuild your base image, right? So then you got to go talk to Dirk and Carl about how to do that. Okay, cool. So, any more questions? Any more comments?
So,
No?
you
Oh,
know,
yes.
if you had several images running, they would all be on the same IP.
No.
Right, the wrong one.
No, they will assign separate IPs to them, I believe. So when we did, what did we do? What was the command that we used on Macs? Do you remember? Docker ls, like that. You'd have multiple different stuffs with different IPs. I believe, I think. That said, I never actually tried to use more than one at once because I want to assign all my resources to one to make it as powerful as possible. But that's just me.
We'd like to know how to kill all the running images.
You want to kill? Okay, you're ready for this, eh? Okay, so Okay, let's do this. So what we've done so far is spool up an image with some custom dependencies on it and list what we have and kill what we have. Everyone is super keen to know, how do we get rid of all of this all at once? So it's with a little bit of shell magic. We do docker remove -f flag for forks, because we're not even going to bother killing them. A little bit of shell magic with a shell variable, dollar brackets, oh my god, I can't type today. Docker ps -a -q modifies that PSA to just give you the process numbers, whatever they're called. Fire that off, and it does that, and it should kill everything. If you do docker ps-a again, there should be nothing there. So the command once more was that. With great power comes great responsibility. This kills and deletes all containers. So be aware before you use this.
You can type in Docker.
Yeah, I mean, this is nothing. This isn't really a Docker command, right? This part in the $, that's a shell variable that's taking, here, I mean, let's build it up one step at a time, right? You know Docker ps-a already, got lists. Q, it's not going to do anything right now because nothing is running. So Q just runs or just lists the container IDs. So in that $, variable, you just got a list of all the container IDs, and that sends it to docker remove -f. It's actually shell magic. It's not really anything to do with Docker there. Okay, cool. Sounds good. So what have we done so far? We've used a base image to get our operating system and basic dependencies set up. We've installed a custom dependency on top of that. That's all super cool. And we started in stop containers. That's all super cool, but of course it's not actually useful until we can actually use those dependencies to run some code and do some analyses. So what we like to do next is use that dependency stack that we've made so far to run a piece of code that's living on our physical machine. Okay? And I recommend keeping those dependencies separate. So like your dependencies encapsulated in your Docker image and your code separate on your machine so that you can mix and match them however you want. Anyway, so how are we going to do that? Before we do, we need a convenient script that we can run on the stuff we've made so far. So let's open up a file called gapminder plot.r. And now if you look in the tutorial stuff, at the link on the backboard and the link that I posted in the chat for those of us joining us on the internet, there is in section 3, if I can find it again, not there, where'd it go? In section 3, there is a script from Jenny Bryan that makes a cool plot on the Gapminder data. So cut and paste that whole thing into this new file that you opened. Grab that, fire it off in there, save that, done. So it's this URL and then this script that's at the start of section 3.3. I'll pause for a second while everyone catches up with that. Everyone's staring studiously at their computers. I'll assume you need more time. That's okay. Got it? Got a script? Unresponsive. I'll take that as a no.
Sorry about the snippy thing.
Mm. Going once. Going twice. Okay. So now we've got this beautiful piece of code that we have. And what we want to do, like I advertised to begin with, is take our Docker stack of dependencies that's living in that virtualized little universe of that Linux container and run the code living on our actual physical machine using that stack of dependencies. Anyone want to hazard a guess as to how we can do that? Anybody?
Is it copy the code over the S copy or something?
That's a good guess, and we're going to do that not too long from now, or something similar to that.
I feel really bad for suggesting this, but can't we just go in the RStudio menu and hit like open file and run
Can you?
I don't think you can,
it?
Why not?
because you're not in that RStudio session. You're not on your computer.
You're in the magical bubble universe of Docker. So if you try and open a file from there, you're not going to see it doing that. But what we can do is mount a directory from our physical machine onto our virtual machine. So anyone that's not familiar with that, that's just like mirroring a directory across two places. So like we're going to have access to the same directory from two places. And how we do that is we're going to launch our image in the same way we did before, but with a new argument. So we're going to add in after the port -v. Oh wait, hold on, sorry. Before we do that, give yourself a PWD to find your present working directory on your machine. And then we'll do what I said we were going to do.
You kill our existing process first.
Yeah, do that. Remember the one to kill everything and kill them all and delete them all? Is this command right here. So shut them all down, that command. Okay. And then, third time's a charm here. There we go. -v, cut and paste in that directory that you saved your script in, and then colon with no spaces or anything, and then exactly /home/RStudio/. And what that will do is mount or mirror the directory that you got from PWD with the directory home/RStudio inside the little Linux container bubble universe.
Would it be so magic you to do like little $sign WD inside brackets?
You could probably do that if you're fancy. Go for it. Go for it. You should do it. You should do it. But if you're not fancy like me, you can just cut and paste stuff. Fire that off. Big ugly hash. Back to our browser. Refresh there. RStudio to get back in. And now, if we look in, you might get a warning like this if you didn't shut R down, but it doesn't matter. Whatever. Fire up R again, and lo and behold, look at what is in the file section here. All the stuff that was in that directory that you mounted when you started this. So now, your little bubble universe of your Linux container has a window onto a directory on your actual machine. Load up the plot by clicking on gapminder plot R. How do we do this? How do you do this, R people? It's like code, run region, like source. What? No, I want to run all. Oh, the stupid Google Hangouts thing is in my way.
Source runs everything.
What? It does it?
There's a little button in the upper right-hand corner.
Yeah.
Source.
I believe you. Is it doing anything?
Yes, it did it all. Should have done it all.
I don't think I believe you. I don't think I believe you. This worked for me when I did this when I practiced it.
Command A to select all the codes. And return to run all the codes.
I believe you, but I'm gonna do it. No, come. Oh, that's terrible. It just cuts off that menu. Okay, let's do it your way. You said Command A,
Yeah, select all the codes.
but I want.
You have to be,
Yep.
And then command return.
Aha! Success! We get the plot that script wanted to generate. A couple things to appreciate and reiterate here. We didn't actually read anything about the script, but if you dig into it, look, it's relying on dplyr right there, and it's relying on ggplot2 right there. All of which we got with putting exactly 0 effort into it, just because they came to us as part of that ROpenSci image that we started on. So cool, we've got that, and not only do we have that, we got that by taking that dependency stack that's in our virtual machine and running it on code that lives on our physical machine. So I know I know I said Docker was like a pie a minute ago. Now it's like a lens. Now it's like a lens that you can look through at any code you have and run that code in the appropriate context as defined by that image. Make sense? Questions?
Yeah.
Andrew, then Jeff.
So you could just make sure I understand this. So you could like have a large, instead of a single R scripting, be a large directory filled with data and all this stuff.
Mhm.
You can just run it
Yep.
in a clean environment
Exactly.
to make sure that it would work on someone else's machine.
And that's the other beautiful thing about it is exactly what you just called out. It's always a clean environment. You don't have to wonder if this plot you just got is because of, I don't know what other stuff is installed on your machine.
Right.
because the only thing installed on your machine is what's in your Docker
you
image.
forgot that your beautiful ggplot theme is stored in your R environment, and you
Cannot happen. Cannot happen with a Docker image. So.
So basically, when we kill an image or something, so we're done, do we lose, even if like, we mount stuff, does the changes we make in the directory stay there? Like say if we export like a figure or something,
So
is that gone?
no, the way you set this up now is the other beautiful thing about this is, of course, you're going to do all this work inside your Docker image. You don't want all your stuff to just live in this image forever, right? I'm sure you're going to want to get your results out onto a file that is just on your normal computer that you're familiar with. That is exactly what will happen if you save your results to this mounted directory. It will. It
Okay.
comes outside of the little Docker bubble universe, and it's just hanging out on your
So
real computer.
Everything outside of our mounted directory, though, if we decide to save it somewhere else or something, is
No,
gone.
you got to save it in
Yeah.
the mounted directory. Yeah, you move it later, but or mount more directories. I don't know. But yeah,
But yeah, so changes between like you make to an image while running it don't persist. So like the next session.
they persist to your main machine. If you mount the same directory again, you'll see those files you saved the last time.
No,
if,
I'm
if
just-
however, sorry, yeah.
Yeah, I'm just saying, like, say if you've you modify an image or something, or you're playing around an image, and then you didn't mount any directories at all.
Mhm.
Next, and you kill the image. Then when you boot it back up again, do you see any of those changes?
Yes, asterisk again. So yes, you can persist changes from image to image. It is not as simple as just saving at the saving a file here. I
Yeah.
tried doing that for part of this demo and it did not work. So there is something more subtle you have to do. Again, when I was talking to Carl about this lesson, he was like, make sure you tell people that when you delete your container, you delete all the changes you made to that container. So it is possible to persist changes inside one of these containers or one of these images. As a early user of Docker, I kind of like the separation of powers though, of dependencies in the image and like static files on your machine.
Yeah, I was actually sort of hoping everything disappears when you're done. So
It will, this way it will. Yeah, yeah. You can make it not do that though, if you want something else to happen. Okay, cool. So that's what we did. More questions?
Yeah, I know that's one more.
Yeah.
Suppose the directory was version control, the one that you mounted.
Okay. Yeah.
That would I get a little git tab inside the R, making commits from inside the Docker image to a mounted directory? That seems weird. Try it.
You could,
I
it might work, it probably works. You will certainly, okay, well, you will certainly see the .git directory. That will certainly be there because you're just mounting the whole directory.
Right.
If you try to use RStudio's onboard Git functionality
Uh-huh.
from there, it might work, right? It might, well, because Git's functionality is completely encapsulated in the executable and the .git directory. So like, it has all the information it needs to work in principle.
Right.
In principle does not mean yes, No, right? So give it a try. We'll
you
see.
should be able to run Git externally, just like on your own computer.
Exactly. And that's how I would solve that problem, is because I know that will work.
Yeah.
Rather,
It would be sweet because often when we're teaching Git, you were alluding to the software carbon thing, like getting Git installed on everyone's computer is like,
Okay.
but then again, it's like also necessary.
yeah, but you're gonna be part of the Docker image. It's perfect every time. Okay, cool. We've got one more thing to go through in the last 6 minutes of this lesson before we wrap up. So that was pretty cool. What we just did is we took our our stack of dependencies and used it to run some code on our local machine. Sometimes though, we might want to include some static files, be they code or data or README, or I don't care what, whatever, anything, in our Docker image. So an example of when you might want to do that is, what if you want to build a Docker image that's meant to run some code, but that code relies on a parameter file, like a set of configurations, and you want everyone to always have the same set of configurations, you could bake that right in to your pie as the final delicious fluffy egg white meringue on top of your lemon pie as our final layer in our image. So let's do that as our very last thing today. So once again, we will kill all our running stuffs with, where is it? This one. That should kill everything. And then we'll go back into our Docker image. So, what Docker file?
Is that like, I feel like this is like a bad way to kill things. Is that like a correct way to kill a running session?
Did it work?
I mean, it works, but I just feel.
To be fair, I was always a little concerned about the exit code that it gives if you kill it and then PSA it. It's not an exit code 0, which makes me think it's really just
I feel like
smashing
I feel
it.
like it's
But,
not happy with us whenever I do
yeah, but it works. Is there a better way? Probably. But, you know, this is our first lesson.
that.
I want to make it easy to start with, or at least as easy as possible to start with. Okay, so we killed our stuff. And now we want to go back into our Docker file. Where's our Docker file? Pico, Docker, whatever text editor Docker file. So once again, there's our graham cracker crust at the top. There's our delicious lemon filling as Gapminder. To add a final layer of a static file to our image, we can do the following. If I can find it again. Where'd it go? Where'd it go? There it is. So add, and then we'll just say any file you want to add, file name there, I'll call it data.dat. So that's the file from your local machine you want to add to your image. And where do you want to put it in your image? Let's put it in the same place we've been doing stuff, RStudio, like that. Control out, line like that to add a static file. And again, this could be it. It could be code, it could be data, it could be README, anything you want, absolutely anything. So once you've got that, it's obviously not going to work unless we actually have a file called data.dat. So let's pause for a second while people copy that down. And then open up a new file. I'll go back there in a second if people didn't get it. And then put anything you want in here. Doesn't matter what. I'm a JavaScript guy, so I'm going to say JSON is awesome. Doesn't matter. Anything you want in this file. Out of there. I'll go back into the Docker file in case you didn't finish copying there. So that's that. So what this final line is going to do is it's going to add data.dat as a static file to our image. Copy, copy, copy. Okay, then to build that, we do the same thing that we've been doing. Keep on hitting up arrow until you find Docker build-t lemon pie. Fire it off. Notice something kind of cool that you will not notice if you don't read all these lines of gibberish that it spits out. So we built lemon pie a few times now. Step 2 up there, right under it says it's using a cache. Same with step 3, it's using a cache from our previous builds of these images. Docker in the background is actually version controlling all of these images that you're building. And it's smart enough to say, okay, if the instructions in your Docker file right here haven't changed, I'm going to just use those same built layers that we built in previous builds of this image. And I'm not going to start redoing things until I find something new. So in this case, it would be this add data.dat line. So that implies a useful, not crucial, but useful best practice for writing these Docker files. And that's once you've settled on a dependency stack, do not change those top lines. Leave them exactly the same in the same order every time, and then Docker will be smart enough to not repeat itself, not rebuild those. It's not absolutely necessary. Nothing will break if you don't do that, but it'll make your builds faster. That's kind of cool. Okay. Did we build it? I think we built it. Yeah, we built it. And so now we can launch it. And now let's launch it without the mounting this time, because we want to see what we actually put in that directory. So we'll go back to our original launch command, which is docker run vp a787:a787 lemon pie, like that. fire it off. Clearly hash. Back in here. Kicks us back to the sign-in page. RStudio. Like so. Sign in. Now what do we see? In files, aha, there's our data.dat exposed to us in our image, but notice there is nothing else in this files folder because we did not mount that directory like we did last time. So we're only getting, in this case, the static file that we baked into our image. Drawback, I can't see the stuff that's on my computer. Benefit, every time I hand someone this image, they will have data.dat exactly as I baked it in to this image. So if that's something that's important to you, you want to distribute files along with your Docker image, that's how you can do it. So that's it, only 1 minute over time. That is what I wanted to tell you all about Docker today in terms of commands and ideas. So what did we learn? Today we learned that Docker will run an operating system and a stack of dependencies in this encapsulated little environment inside a Linux container on your machine that you can distribute to anyone you want, including yourself in the future. Is that my time up alarm? Get off the stage. No. That you can distribute to all your colleagues or yourself in the future to run things the exact same way every time. We learned how to use a base image. We learned how to install kind of static files on top of that. And we learned how to manage our running containers and images. Questions? Jeff?
How many, so does it have like, I mean, this is, I've got like a specific idea for this in mind right now, but does it, you have the same number of processors available for your virtual machine as the computer you're running it on?
You can assign whatever resources you want.
Okay. And like how would you go, like say adding this to like something like Amazon Web Services or something?
That's the thing I wanted to wrap up with. We are now on the doorstep of doing all kinds of cool stuff now that we've encapsulated our dependencies in a Docker image. So as I already alluded to before, I keep talking about sharing these things with people. How do you do that? How do you actually share these things? Well, you all downloaded this Rocker R OpenSci thing from who knows where. I just told you to do Docker run that thing, and it poof magically downloaded it. Well, where it comes from is this awesome place called Docker Hub, which very creatively named is GitHub for Docker images, and it works pretty much the exact same way. So if you want to go find useful stuff, you could search for whatever you want. I'm going to search for Python, and here are 4,338 Python images that I can run cool Python stuff from. That's 8 more than there were 2 hours ago when I finished practicing this lesson. So there's lots of activity in these channels. So you can grab all kinds of stuff you want from here, just like you grab source code from GitHub. You can also push your images up to here, share them with your colleagues, with your friends, with your family, because who doesn't want images of your dependency stack? As Jeff asked, there's all kinds of places you can also use these Docker images. For example, Amazon Web Services. So AWS makes it really easy to spin up a Docker image on EC2 or any of their cloud computing services. So rather than having to figure out, okay, what kind of machine am I running on EC2 and how do I get set? No. Get your Docker image up on EC2 and it'll work exactly like it did on your machine. So if all of a sudden you decide, I need 60 processors really fast, you can have them for super cheap on AWS, and it'll all run the same way. Same story, if you're into continuous integration, Travis will run Docker images in their CI server. So people that don't know continuous integration, the idea of that is you write a bunch of unit tests to make sure your code actually does what you think it does. And every time you push to GitHub, a service like Travis will grab your code, run all your tests, and shake its finger at you if any of your tests break. So you get an automatic warning if you've broken anything. Of course, for it to be able to do that, it has to be able to run your code. Docker makes it super easy for Travis to run your code. In practice, and disclaimer, this is purely personal opinion, the hardest thing about continuous integration is getting my code to work on Travis's servers. Docker makes it easy-ish, right? As easy as it could possibly be, because it'll run the same way on their servers as it does for me. And all kinds of other cloud services support Docker as well. So you are now on the doorstep of being able to run your code anywhere you want, have consistent performance no matter where you go. That's it. That's what I got. Any closing questions or comments?
Yeah, I missed your answer to his question about running the actual guest OS or shell. How do you get to the shell? So
Right.
So it's basically fixing things that it fixes.
That's okay. So to run in the shell, if I would recommend if you want to see that, go through the basic Docker tutorials right on Docker's website, because that's the default behavior. This RStudio shell is actually kind of a fancy thing that uses that shell to launch RStudio in the browser right away. So, and it doesn't background that process. So it's just taking up the shell. Every single other, for the most part, to first order, Docker image will launch and immediately give you back the shell.
So I tried to run the Ubuntu
Mhm.
image, and it was killed. Why is that?
It was a terrible image. I don't know. Was it the official Ubuntu release image? I don't know. I mean, there's bazillions of images.
I don't know why it's on my machine, but I list images. So I don't remember.
Oh, really? That's interesting.
It is installed, so.
Oh, I didn't get any images by default when I installed Docker. But as you can imagine, just as there is some extra special stuff on GitHub, there's extra special stuff on Docker as well. It may not actually work all the time. So, buyer beware.
So sorry, one more question.
Yeah.
When exactly does it run in VM, and when does it? It doesn't run VM. It uses the
Yes,
host operation.
it runs a VM for you and me. It runs a VM on OS X and Windows.
But let's say you're running, I don't know, you're running Red Hat machine, and you want to start a centralized image. Will it run in VM, or will it just use Red Hat?
I think it can run CentOS inside a Linux container on that Linux
Let's say
machine.
you have a Debian machine, and we try to run Red Hat container. Will it run Desperate system in the VM? Or?
That's my answer to every combination of Linux builds is going to be the same. That's a. The reason Windows and OS X need a virtual machine is you need some Linux build so you can have Linux containers. I was from the brief docs that I read on Linux, using Docker on Linux, it seemed like you just didn't need that, and it could just run whatever image you wanted inside a Linux container.
It's important in terms of efficiency, right?
Mhm.
Because you don't really want to run VM for experience and stuff.
The like I said, the impression I got was that it does not run a VM on Linux machines. More questions, more comments?
I'm just going to throw out that there is a Docker stop image that gives you instead of 0, whatever.
Cool. Then you should probably use Docker stop. Put it to bed nicely rather than just pushing it off a cliff.
Are there good examples of trying to understand how so I'm versioning from code on GitHub, and I want my project to be reproducible everywhere and to exist in this state even after versions of R change and packages to improve, blah, blah, blah. So I want a Docker file associated with it. Do you simultaneously push a Docker file containing your dependencies, like the sources of the packages, to Docker Hub, and then how do you associate that with the GitHub repo? What's the best practice?
Right. So a couple things. I mean, I don't know if there is one single official best practice, but a couple things you can do is include your Docker file in your GitHub repo so that at very least you can rebuild that context if you have GitHub. The other thing you can do is that you can add metadata to both. Right. Your GitHub repo can say, go look at this Docker Hub repo. Docker files can contain either comments like we did or annotation commands that will add metadata to that Docker file that says, go look at this GitHub repo to associate the two together. I would say the best practice at the moment is like the triple threat of GitHub, Docker, and Figshare or wherever else you want to put your data so that you can reproduce all three of those things. If you have those things, you have your bases covered. Pointing at each other is a question of metadata. Nobody has a good answer to the question of metadata.
Right.
There are many working groups on the question of metadata.
Yeah, like I'm seeing that the Docker file, you get the version of the R package you're downloading.
Mhm.
So that sort of archives some of it to the Docker file, but then CRAN will eventually no longer carry that under 0.1. It'll eventually forget about it.
Really?
I think so. In 20 years from now,
Yeah.
when it stops breaking, Jenny's not going to maintain every version of the package. I
But
don't know.
you can just have a legacy version. Well, I have no idea. I don't know how CRAN works. Right? Like, I'd be shocked. Like, why not just let the legacy version sit there? But what do I know, right? I don't know. I don't know how CRAN works.
Anyway, very cool.
What does the Rocker package actually do for R? Because I know you mentioned this as like Rocker, and there's like a package for Rocker, called Rocker. I just have no idea what it does because we've never really touched it today.
Well, we did actually. So what we used was the Rocker /R OpenSci image. So Rocker maintains a whole bunch of different images for using with R. And Rocker's like a collaboration. It's like Dirk and Carl and a few other people.
So it's
who
not.
work on
Is
this
it
stuff.
actually? It's I guess it's not
Venmo.
actually a package per se, but just I guess a bunch of R.
It's a
images.
I would call it a collaboration that produces a set of Docker images.
Okay, so okay.
So like there's another one that does not have the R OpenSci stuff on it. So it's exactly the same, but no R OpenSci. I think there's an even more stripped down one. There's a few others.
Okay, good. Yeah, I was under the impression that it was an R package, but I guess it's a series of Docker builds.
No, it is definitely not an R package.
Right.
Any questions from the internet? I can figure out how to use this thing.
I love when it does that.
Yeah, it's fantastic.
Very good.
And hold on, I'm gonna type it here. Any cues from? I don't think anyone's actually on this, so whatever.
It says one viewer.
Oh, there's a viewer. Oh, cool. Hi, viewer. Going once. Any more questions from the room while we wait for the internet? Nope. Okay. I guess that's our Docker tutorial. So last thing for study group of the year, we have, what do we have, Amy? We've got a party on Friday. Hooray. We're all going to meet up at St. Augustine's on Commercial Drive at when? 6:30? 6? 6 on Friday.
Some random thoughts. There's an issue open on the, on our GitHub repo, so we need the details there.
Yep. Hope to see you all there. Bring your friends. Thanks for coming out, everyone.